All right. Okay. What are we doing today? Good question. What should we do today? So I know these classes started talking about the combinatorics, counting stuff. Varn's class is about to, whoops, get there. Probably on Monday, maybe today. I don't know. He was telling me yesterday. I don't remember what he said. If he's starting talking about today or Monday. So I guess I should start with, are there any things that we need to, need to or want to talk about as far as concerning all the stuff we've been doing with all the linear systems of differential equations or the nonlinear? Yeah, sure, sure. Let me take a look. So I guess, yeah, so I guess the idea for today is if you've got questions, we can go over them. And then if we're done with all your questions, we can move on to talking about all this counting stuff. So I guess I could write things as Co-17C. Today is the 16th. Yeah. And here's the setup. We want to find the equilibrium for this system. X1 prime of t is equal to negative 6.2 plus 1.1 x. I'm going to say that's x1 instead of y, but yeah. x1 minus 0.8 x2. And the second differential equation is x2 prime of t is equal to negative 13.8 plus 2.1 x1 minus 1.2 x2. We're also given the initial conditions. X1 of 0 equals 11. X2 of 0 equals 4. So here's what I would point out about a system like this. First of all, it is linear. We know it's linear because you only have your variables multiplied by constants, right? You don't have a variable squared, you don't have a variable cubed, you don't have a variable times a different variable, right? We just have something times x1, something times x2 in each equation. But it's also non-homogeneous, right? You've got that constant term added in one or both of the equations. So your equilibrium definitely isn't just going to be the origin, or at least probably won't be the origin. It's not, right? If you plugged in 0 for x and 0 for x2, you wouldn't get both equations equal to 0. But what I want you to think about here is the fact that since these are both linear equations, they're both just lines, right? If we set each of these equations equal to 0 and think of x1 as x and x2 as y, it's just a line. And so is that. And so all we're really doing when it comes down to it is trying to find where these lines intersect, which shouldn't feel too daunting, right? We're just trying to find the one point of intersection. There should only be one, unless the lines happen to be the same line, which there is a problem. There's a gap problem where you have to do that. It's kind of weird, where one of your eigenvalues is 0, but we can talk about that one too if you guys want to. So looking at this, if we set each equation equal to 0, it's kind of gross, right? We've got these decimals. They're not making it very nice. If we wanted to, we could start just by multiplying each equation by 10. I might do that. There's nothing wrong with doing that. Yeah, I think I would. I'm going to write this as negative 62 plus 11x1 minus 8x2 equal to 0, and negative 138 plus 21x1 minus 12x2 equal to 0. And as always, when you have a system of two equations and two unknowns, and they're both linear, you can either choose to solve them by substitution or elimination. Or I guess you could even use matrices if you really wanted to, right? So there's three ways you could do this. One way would be yeah, let's do the matrix thing first, because I think the matrix thing is kind of worthwhile. So if you want to solve this using matrices, you're going to rewrite it like this. You're going to keep all of the x1s and x2s on one side of the equation. So we have 11x1 minus 8x2 equal to positive 62, and 21x1 minus 12x2 equal to positive 138. So then we can rewrite this as a matrix equation. 11, negative 8, 21, negative 12, times x1, x2 equal to 62, 138. And then to solve this equation, we're going to multiply both sides by the inverse of that matrix, which should exist. Well, I assume it exists because I'm pretty sure the determinant of that matrix is not 0. 11 times negative 12 minus 8 times, yeah, that's definitely not going to be 0. So we could solve this by saying that x1, x2 is equal to, if I call this A and this B, it's going to equal A inverse times B. All right, A inverse is kind of a pain, but no more of a pain than doing it any other way, right? This problem is just not nice either way you do it, so suck it up. So we're going to get 1 over 11 times negative 12 minus negative 8 times 21. And then for the rest of the inverse matrix, we change or interchange the diagonal elements. So the negative 12 is there, the 11 is down there. And then the off diagonals, we change their signs. We have a positive 8 there and a negative 21 there. Times 62, 138. Hopefully the person writing this problem thought about the numbers and it's going to come out beautifully. I don't anticipate that, but it could. You never know. So, all right. So 11 times negative 12 is negative 132. And then 8 times 21 is 168. I mean, you can use a calculator, right? Like I'm doing this by hand because that's what I've got, but I'm about to not because 12 times 62, why take chances? So let's see. So over here, we're going to get 12 times 62, right? 12 times 62, or I should say negative 12 times 62, and then 138 times 8. So that's going to be negative 744 plus 1104. And then the second row is going to be negative 21 times 62, which is negative 1,302 plus 11 times 138. Gosh, these numbers are gross. I mean, I guess I made them gross. No, I don't know. Didn't really make them grosser. They just wouldn't feel as big. They'd still be just as gross decimals. You just have a decimal place separating it, making it feel less big, but still disgusting. Plus 1,518. Okay. So let's see. So negative 132 plus 68 is 36. And then 1104 minus 744. I should be able to do that in my head, but some days you just want to don't think it's oh, look at that. It's 360. How beautiful. We're on track here. And then I'm hopeful for the next one too. 1518 minus 1302 is 216, which I think is 36 times 6. So multiplying the 136 through, I believe we get 10, 6. That worked out nice. So what that means is our solution is x1 equals 10, x2 equals 6. And if we wanted to, we could check, right? If we actually plug in, just to be sure, like right here, 11 times 10 minus 8 times 6 is 110 minus 48, which is 62. And 21 times 10 minus 12 times 6 is 210 minus 72, which is probably 138. Cool, it worked. I mean, obviously it should have worked, but I will say when the numbers are sufficiently not nice, I would say this qualifies, I would do it this way, writing it as a matrix equation and then solving it by multiplying by the inverse, instead of trying to eliminate either the x2s or the x1s. So we could probably do this with elimination not too badly if we try to eliminate the x2s. So let me just show you that one as well, just so we can see it one more time. So we could take this equation, 11x1 minus 8x2 equal to 62, and 21x1 minus 12x2 equal to 138. And I'm going to multiply the first equation by negative 3 and get negative 33x1 plus 24x2 equal to negative 186. And the second equation by positive 2. So 42x1 minus 24x2 equal to 276. We're going to add these equations together. Negative 3 plus 42 is 9. Those are 0. Negative 186 plus 276 is 90. So we do get x1 equal to 10. That did feel easier to me, but take your pick. And then if we plug back in x1 equal to 10 into either equation, like the first equation, 11x1 minus 8 times 10. Sorry, I said 11. I said x1 is equal to 10. Apologies. 11 times 10 minus 8x2 equals 62. So 110 minus 62 equals 8x2. And then 110 minus 62 is 48. So 48 divided by 8, which is 6, is equal to x2. So that gets you there as well. I don't know. They both kind of feel terrible, but they're not, I mean, in the world of numbers, they're not that bad. What was the question? Find the equilibrium. So we found the equilibrium, and I would write my equilibrium as x1 hat, comma x2 hat, because that's the notation we often use for equilibrium, is 10, comma 6. Now let me ask you, is there anything else Ross to do with this setup? Yeah. Okay. Oh, so describe the trajectory, which I believe means like, say if it's a saddle or a, okay. So looking back at my system, so this is actually where, yeah. So I probably should, yeah, I guess oh gosh, words. So to describe my trajectory, I'm looking at my, again, my initial without multiplying by 10 system of equations, which is equal to, I'm going to write it like this. Instead of writing it as negative 6.2, et cetera, et cetera, et cetera, I'm going to write it as the matrix 1.1, negative 0.8, 2.1, negative 1.2. That matrix multiplied by the x1, x2 vector plus the negative 6.2, negative 13.8. And again, I will just say, we know that if we plugged in 10 for x1 and 6 for x2, that this whole thing would equal to 0, 0. Now, if you're trying to solve the system or find the trajectory, what we did last time with a non-homogeneous system of differential equations is we did this whole variable change where we said like y1 was x1 minus the equilibrium, y2 is x2 minus the equilibrium. And through that whole process, you end up just getting the same matrix to describe your solution. So I think we can skip all that. I'm happy to talk about it if you want me to, and just say what the solution is going to be. So we'll come back if we need to. So looking at our matrix here, so I would probably first try to do it the easy way. No, yeah, maybe. No, I guess not. I don't know. I would look at the trace real quick and the determinant. My determinant is 1.1 times negative 1.2 minus negative 0.8 times 2.1. So let's see. 1.1 times negative 1.2 is like 11 times negative 12. The negative 132, except it's really negative 1.32. Similarly, 8 times 21 was 162, 8. So 0.8 times 2.1 is going to be negative 1.68. So it's going to be plus 1.68. And I'm disappointed because my determinant is positive, which means I have to do more work. So I get 0.36. And then my trace is 1.1 plus negative 1.2, which is negative 0.1. I'm also disappointed. Well, not disappointed, but so here's what I know so far. I know it's stable. I know it's not a saddle. And I know I'm on the stable side of that picture. If we really want to just stick with doing it using that kind of graphical method, all we really have to now answer is the inside of the square root that would come from doing the Pythagorean theorem, the other formula whose name I can't remember at the moment. Thank you. Is that inside of that square root positive or negative? If it's positive, we have a stable node. If it's negative, we have a stable spiral. So I'm going to look at my inside of my square root, which is the trace squared minus 4 times the determinant. And that's equal to negative 0.1 times 0.1, sorry, times negative 0.1, minus 4 times 0.36. And I don't really need to go any further. I can tell for sure that's going to be negative because that part there is pretty small and we're subtracting something that is much, much larger than it. So that's negative, meaning we have imaginary eigenvalues, complex eigenvalues, and we know that the trace is negative, so it's got to be stable. So we have a stable spiral. Now, I should point out, if we were asked to find the general, we're not going to find the solution here because it's terrible, right? It's the whole imaginary eigenvalues, imaginary eigenvectors, cosine of I theta garbage. They didn't ask us to find the general solution, right? Oh, right. So the other way you could do this is you could actually find the eigenvalues. It's the same work, really, just in a different context. That's all I have to say about the one, really. I think you're like checking to make sure it's right. Oh, no. It's fine if you do. I don't care. No. Oh, yeah. So if it's a stable spiral, is it spiraling clockwise or counterclockwise? Oh, whoa, 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 whoa. That's a terrible question because it could be either. Is it spiraling inward or outward? Inward, because we're spiraling inward towards the origin, towards the inward towards the equilibrium, which is 10 comma 6. But it's definitely spiraling inward. But what about the direction of our turning? So we're definitely spiraling inward because of stability. But now the question, clockwise or counterclockwise? Oh, interesting. So, yeah. So I think what we need to do, this is a little interesting here. This is going to be terrible. So here's what I would do. So normally what I would do is I pick like the 4 points around the origin and then plug them into the initial equation and see which way my arrows are pointing to see if it's going clockwise or counterclockwise, right? That looks like to you guys? Yeah, okay. So, but the problem is the origin is not our equilibrium here. So what we need to do is actually look at plugging in points around our equilibrium, which is 10 comma 6. So that's what we're going to do. So we're going to look at, yeah. So back to our equations here. I'm not going to write them down again. I'm just going to pretend like they're right there so I don't have to write them down again. But what we're going to do is we're going to say, okay, well, we're looking over here at 10, right? What is 10 for x1? Yes. And 6 for x2. So that's our equilibrium where we're spiraling inwards towards, and our only question is, are we spiraling inward like that or inward like that? Like, are we going clockwise or counterclockwise? So I'm going to pick, I usually like to pick points that are like here, 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 and here around it. So the points I'm going to plug in, which is going to be kind of a pain, are going to be 11 comma 7. Yeah. Okay. Yeah. 11 comma 5, 9 comma 5, and 9 comma 7. Eesh. Okay, it's gonna be a little bit gross. Yeah. So, right. Yeah. Ugh. Yeah. Ugh. This is a lot of work. Okay, so plugging in 11 comma 7, we're gonna get x1 prime equal to negative 6.2 plus 1.1 times 11 minus 0.8 times 7 gross. And the derivative of x2 is negative 13.8 plus 2.1 times 11 minus 1.2 times 7. Yeah, so time for a calculator, I think. I mean, sure, why not? So this is negative 6.2. 1.1 times 11 is 1.21. 0.8 times 7 is 0.56. And then if we add those together, we get negative 6.2 plus 1.21 minus 0.5. It's gonna be negative for sure. So negative 0.57. So we get a syntax error because I'm not writing the right buttons. Negative 5.55. And the other one is going to be, I feel like I made a mistake here. And you shouldn't feel bad for letting me get away with it because I was going kind of fast. 1.1 times 11 shouldn't be 1.21. I got the decimal in the wrong spot. There should be 12.1. Let's revisit that there. That's a 12.1, and that's a 5.6, not a 0.56. Apologies. So that looks more sensible. We have negative 6.2 plus 12.1 minus 5.6, which is going to be 0.3. Okay. And similarly here, we're going to get negative 13.8 plus 23.1 minus 8.4. So that's going to be 23.1 minus 13.8 minus 8.4, 0.9. So at the point 11.7, which is right here, we're going right 0.3 and up 0.9. So we're going more up than right. So we're going kind of like that way. Now, here's what I've learned over the years doing this. Typically, the line, like kind of like the line that makes a 45-degree angle with your equilibrium is kind of the deciding line. So this line right here, that's like the line kind of y equals x except shifted some way. If my arrow was pointing below that line, it would be going clockwise. But since it's pointing above that line, it's tilting me back the other way and going counterclockwise. And the only reason, so usually I would plug in more points, but you can see it's going to be terrible to do that. So I'm fairly confident that this is going that way, which is counterclockwise. And there is, I remember when I first taught 17C, trying to figure out like how do you determine this looking at the matrix? And there is a way, which I never remember until after I've done it, which is that if you look at the matrix and you know that you have a spiral, this corner up here, whether it's positive or negative, should tell you the direction it turns. Now, that's not the works anyone wants to see on an exam, but here I could have said now that I know, okay, if it's a spiral, if it's a negative up here, it's going to be whatever direction we just got, counterclockwise, and if it's positive there, it should be clockwise. And we could probably go back and look at other examples we've done in class to verify that. We meaning you all. Yeah.
If you still get the same answer, we can plot like 0, 1, or like.
So good question. So well, in fact, if I plugged in 0, 0 over here, what would I get? Well, if I plug in x1 equal to 0, x2 equal to 0, I should get x1 prime equal to negative 6.2 and x2 prime equal to negative 13.8, meaning I'm going left and down, but more down than left, almost like twice as much down. So I'm kind of going that way, which, I mean, you could probably argue tells me you're going the same direction, but it's a little harder to tell because we're not like we're kind of above the what I think of as the dividing line. So I don't know how helpful that is to pick a point off there. Yeah, yeah, yeah. So I would mention, I guess I could say that if we actually did the whole change of variable thing, then your system would be recentered around the origin, and then you could use the nicer points. So maybe that's worth doing in this context, but I don't know. It all seems like a terrible pain, to be honest. I know that's not any solace to you all because you still have to do it, but yeah, yes.
Yeah, you have like switch like substituting variables or not.
So you mean to find whether it's to find what kind of trajectory we have. So what I would point out is when you're doing the substitution of variables to change like to y's or whatever, you still end up with the same matrix. So in fact, let me show it because I do think it's worth being aware of what's happening here. So here's the work that we didn't do but could have done. So instead of kind of sticking with this, we could have said, okay, well now we're going to let y1 equal x1 minus the x1 coordinate of the equilibrium, which is 10, and y2 is going to be x2 minus 6. So then my old system, oh yeah, so, and then also we need x1 equal to 10 plus y1, x2 equal to 6 plus y2. So then what we get to say is that dy1 dt, sorry, it always feels like I'm relearning it every time I do this. dy2 dt, well, the derivative of y1 is just the derivative of x1. It's always true. This always works out this way whenever it's non-homogeneous. And the derivative of y2 is the derivative of x2. And then we know the equation for the derivative of x1. It's the original equation we started off with, which was terrible, terrible numbers. Yeah. Negative 6.2 plus 1.1 times x1 minus 0.8 times x2. And this one was the other equation, negative 13.8 plus 2.1 times x1 minus 1.2 times x2. And then we plug in what x1 and x2 are equal to in terms of y. So this is going to get dicier for a minute. Negative 6.2 plus 1.1 times 10 plus y1 minus 0.8 times 6 plus y2. If you've done this right, here's what should always happen. You should only be left with a multiple of y1 plus a multiple of y2, and the constant you're adding on should end up being 0. That is the whole point of this process. So if we simplify this, it should come out to be 1.1 times y1 minus 0.8 times y2. And the negative 6.2 and the 1.1 times 10 and the negative 0.8 times 6 should add up to 0, and they do. Because negative 6.2 minus 4.8 is negative 11. And similarly, this one should end up being, I'm not even going to show the work, I'm just going to say it's going to end up being 2.1 times y1 minus 1.2 times y2. That should always happen when we do this. So then your new variable change system is exactly dy1 dt, dy2 dt equal to the nicer matrix, well, the same matrix actually, 1.1, negative 0.8, 2.1, negative 1.2, times y1, y2. And this system has just shifted the equilibrium over to the origin, has 0, 0 as the equilibrium. And so then I'll point out if we're trying to talk about the trajectory of our equilibrium here, it's still just looking at the matrix, which is the same matrix we already looked at. So you could do it using the trace determinant, or you could go find eigenvalues, right? We could say, yeah, but it's just, okay, it's determinant of, the usual fun thing, which is going to end up being kind of gross, but it's 1.1 minus lambda times negative 1.2 minus lambda minus negative 0.8 times 2.1. These numbers should look familiar. So we're going to get lambda squared. We're going to get plus 1.2 lambda minus 1.1 lambda. So that's going to be a minus 0.1 lambda. And then 1.1 times negative 1.2 is negative 1.32 plus 0.8 times 2.1 is going to be a number, 1.68. And so then we end up getting lambda squared minus 0.1 lambda minus 1.32 plus 1.6 is plus 0.36. And we see the same values coming up again, right, that we used when we found the trace determinant thing, right? There's the negative of your trace, right? Our trace was, sorry, there is our, giving me pause. Sorry, I have to think for a second. Plus 1.2 lambda minus 1.1 lambda should be plus 0.1 lambda, because the coefficient of lambda should be the opposite value of your trace. Our trace is negative 0.1. Our coefficient of lambda is positive 0.1. And then this value over here, 0.36, is the determinant of the matrix we found before. So then if we want to find the eigenvalues, set this equal to 0, you use the quadratic formula, and you get negative 0.1 plus or minus the square root of 0.1 squared minus 4 times 0.36 all over 2. And we can certainly see that the inside of that square root is negative, so we have complex eigenvalues, and we have a negative real part, so they are stable complex or stable spiral things. Whew, it's a lot. Did you follow up? Okay.
So how do you use this or the trace?
You can use either. Either one will get you there. So if you have to find the general solution, you will have to find the eigenvalues. So you might as well do the thing where you have to find the eigenvalues. Because if you use the trace determinant method, you aren't actually finding necessarily the eigenvalues. You're just saying, I know what the trace and determinant are. Yeah.
Do you like multiply everything by 10? But like, can you?
So the only issue with that is that it changes the value of your eigenvalues. Yeah, it does. So that's why I kind of had to go back to the original equation first. It's probably doable, but it can be it's you have to be careful. I'm it's probably okay just to do that, but I don't want to say that without investigating it more, and I'm not 100% sure you can do it without causing some problems. I don't think it should change anything really, but you never know.
Follow question two as well, because it was like, it sounds like the president of prey, and they understand how it's supposed to be prey.
Okay.
Wow. And there was like two other like, um, and no petition, like how would those look?
So what was the last part you said?
Competition and symbiosis.
So they're saying that this original system is representing some sort of predator-prey relationship.
They, well, this was determined, and there was predator prey, like this.
Oh, like if this relationship is representative of predator-prey or of symbiosis or what's the other ones? Oh gosh, like commensalism or competition. Uh, Good question. I don't know. I never think about you're asking me a biology question. This is a math class. No. Yeah, unfortunately, that is not something I really know very well, right off the top of my head without having to do more inspection. And I'm not really sure. We know we have so here's what I would say. We have a spiral. It's an inward spiral. So we're spiraling inward toward. So here's what I would think about this system, right? If we in fact you so I would also point out you are totally welcome to like use a graphing device to look at what this thing looks like. So we could have, and I do think it's worth looking at, even though it's gonna be kind of a pain to type out. Where's my graphing things over here? So if we put these in, they're kind of gross, but fine. We have negative 6.2 plus 1.1 times x minus 0.8 times y. And then the second one is going to be negative 13.8 plus 2.1 times x minus 1.2 times y. And then I'm going to change my window so that we actually get the things on there. So let's go like to 15 into 15. So if we graph this thing, why didn't you? Oh, there's a dumb equal sign in there. Sorry. I'm like, why isn't it working? What's wrong with you? Gosh, this one's so stupid. Okay, there we go. That should work. Finally. Oh, geez. All right, let's look at that. So here's what this thing looks like. So again, over here at 10, comma 6, that's where your equilibrium is that we are spiraling hopefully inward towards. Um, yeah, interesting. But it feels like it's a very kind of slow spiral. Like you really have to do a lot of turns to get in there finally. So yeah, I don't know. I unfortunately I don't really know like what this means. Um, I would say both of our populations are getting closer and closer to the first thing being 10 and the second thing being 6. So, but they're kind of varying back and forth. So, yeah, I don't know. Like when I look at something like this, I think of okay, well, like I kind of think of as like I'm imagining X1 being prey and X2 being predators. So the change of X1, yeah, you're going to get more of the prey if there's prey, and you're going to less of the prey if there's predators. So the amount of predators are taking away from the prey, the amount of prey are adding to the more prey because they're making more deer or whatever. And similarly here, if there's more prey, well, then you're going to get more predators because they have more things to eat. But then if you have more predators, you're going to get less predators because they're taking resources away from other things. So that is one way you could argue, maybe incorrectly, that this is a predator-prey situation. The real answer is I don't know. Right? But I could make a good argument for it. So if this is a BSing your way through it, it's probably worth some points. Um, what's that? It doesn't seem like a great question to ask on an exam, but that doesn't mean it couldn't be asked. People ask all kinds of terrible questions on exams. All right. Are there any other questions about this problem? Okay. Well, so I saw a hand back there first. Oh, yeah. Okay. Well, for no, no, for so if we're done with this one, I see like three different people ready. Like, okay. So did you have a different question?
Yeah.
Okay. Good now. Oh, and so on this. Okay. What do you want to know about this one?
Why, yes, one.
Right. Uh-huh.
I don't think when you say that, that clicks in.
Sure. So here's what we're saying. We're saying that so I have basically just shifted things around. So I've said that y1 is equal to x1 minus 10 and y2 is equal to x2 minus 6. So if I take the derivative of this side, I get the derivative of y1. If I take the derivative of this side, I get the derivative of x1 minus 0. So that's how we get to say that those two derivatives are equal to each other because they just differ by a constant. Okay. Now go ahead. Let's take a look here. What do we got here? Determine all equilibrium points of the following. Oh yeah, I think I was looking at this one with someone else, and I really, yeah. So we've got the following thing. I'm trying to remember how this worked. This is problem 7 from the web work, and I remember trying to help someone with it and not being 100% clear on what they wanted the answer to be. Right? Because sometimes people don't always look at all the questions they assign. Equilibrium solution. We have to fill in those 4 blanks there. Okay. So, yeah, I think we got there. But so here's what I would say we have to do. We first have to solve the system. So, okay. So again, right. So this is a non-homogeneous system of linear differential equations. And we could certainly do the change of variable thing, but I don't think we have to. So I would just point out that yeah, yeah. Now this is where I got kind of stuck last time doing this. Was doing sure we got enough time. Let's go ahead and let's go through the motions of actually doing the whole thing. Oh, thank you. Good call. So, okay. So we can first find the equilibrium. So the equal. Oh, this one. I remember this one. This one was weird because one of the eigenvalues is 0. Okay. So equilibrium. So yeah. All right. So equilibrium. We have -3 y1 plus 3 y2 plus 5 equals 0. And I don't even really want to write the second equation because it's the same. The second equation is 3y1 minus 3y2 minus 5 equals 0. And I guess technically not the same, but a multiple of the first equation. So what this means is we have multiple equilibriums because there's many, many, many solutions to this equation. So if I solve for y2, we've got y2 times 3 equal to 3 times y1 plus 5, or dividing by 3, y2 equals y1 plus 5/3. So this is an equilibrium for any choice of y1. Question. Right. So so here's so let me wait to answer that question. But yeah, so technically there is a whole line's worth of equilibria. So if you try to kind of graph this system, well, if I graph the line y equals x plus 5/3, it's going to look like, let's say that's 1, that's 2, 5/3 is about right there. That line is the line of equilibria, meaning every point on this line is in equilibrium? This is kind of one of those, this is one of the weirder questions in this class, to be honest. And so what's happening there is, and the reason why this is happening is because this matrix is not unique. Or said another way, this matrix has 0 as one of its eigenvalues. So yes, how do we solve? Yeah, interesting. So I think trying to do this whole change of variable thing is not the best use of our resources here. So let's just kind of do the solution in general. So if we try to solve, we try to find our eigenvalues for our matrix, the determinant of -3 minus lambda, 3, 3, -3 minus lambda equals -3 minus lambda squared minus 9, set that equal to 0. I feel like we're going to get lambda. No, we definitely are going to get lambda equal to 0 as one of our solutions. So we're going to get -3 minus lambda squared equals 9. -3 minus lambda equals plus or minus 3. So then lambda is going to equal -3 plus or minus 3, which is going to give us -6 and 0. So those are our two solutions. So normally, when you have two, well, in fact, let's just do the whole. We can find the eigenvectors too. We got 7 minutes. We can probably get through this, or at least get to a place where I can say, oh, I don't know what to do now. So for lambda equal to -6, we're going to find the eigenvector. It's going to be -3, 3, 3, -3 times the thing we're looking for equal to 0, not 0, 0, equal to, holy smokes, James, -6 times xy. It's been a minute. So then we have -3x plus 3y equal to -6x. So we have 3y equal to -3x. So we have the eigenvector 1, -1. And then for lambda equal to 0, we have -3, 3, 3, -3 times xy equal to 0 times xy, which is just going to give you the 0 vector. So then we have -3x plus 3y equal to 0, or 3x equal to 3y. So we get 1, 1 as our eigenvector. But then the whole system has been shifted, right? It's not going through the origin for its equilibrium. It's going through, well, this kind of line. So how do I say this the right way? Lambda equal to the eigenline associated with the eigenvalue 0, that entire line is a line of equilibria, plural, infinite. So if it was a normal system not shifted, what would happen is along this line, the eigenvector, this is my lambda 1, lambda 2, v1, v2. Along the eigenline for v2, lambda 2 equals 0, which means you don't get pushed inward or pushed outward, right? There is no motion of travel because multiplying by the eigenvector, multiplying the eigenvector by the matrix doesn't, or gets you 0, right? So you don't move at all. You're not moving inwards towards the origin. You're not moving outwards, right? This being equal to 0 doesn't give you doesn't mean you get to the origin. It means you don't get any movement. Whereas with this eigenvector, which is this one here, this eigenline, lambda 2 equal to -6 means we move inward. But that's true everywhere. So if you had like a parallel line, you would also be completely moving inward like this. So any line that's parallel to the other eigenline, you just go straight in towards the 0 eigenline, which is kind of funky. So in our system over here, same kind of deal. All of my other my lambda equals -6 eigenline, right? They all go like that, and it doesn't really kind of matter because I said, those arrows are terrible. They should be pointing inwards, not outwards. Now, how does this help us? Good question, James. Well, we know something at least. But now the question was, well, I guess we could write our general solution. So really kind of sometimes you just keep doing things until you feel like maybe you've got the right, like I'm just trying stuff to be really frank sometimes. Like, okay, well, I know how to do a thing, so let's try doing the thing. So eigenvalues, eigenvectors, our general solution is going to be, well, C1e to the lambda 1t times V1 plus C2e to the lambda 2t times V2. So let's say that, sure, lambda 1 is -6. So I'm going to have C1e to the -6 times t times my eigenvector for -6, which was, I think, 1, -1, plus C2e to the 0 times t is 1 times the other eigenvector, which was 1, 1. Now, if we let t go to infinity, that part's going to go to 0 because e to the negative infinity gets really super small. So we're going to get C1 times 0. So this part doesn't matter. I shouldn't be writing it. Plus C2 times 1, 1. So here's what I think. Not 100% sure, but kind of sure. Well, no, I'm not. I'm not that sure. But here's my best guess. I think that means we need a 1, 1 here. Yeah, that seems reasonable because looking at our picture here, we should be oh yeah, we need to be somewhere on this line, right? What our equal, that's what we tend towards if we let things go on forever. We end up somewhere on this line. So this is giving us like the movement along the line, right? And this needs to be some point on the line. I don't know if it needs to be a specific point. I'm going to pick 0, 5/3 because I know that point's on the line. Right? So all we're really doing here is in kind of the most complicated way possible, we're writing the equation of this eigenline. That right? The equation of this line is y equal to 1 times x plus 5/3. Right? This line has a slope of 1, and one of the points on the line is 0, 5/3. So you could also write this much more terribly as the coordinate xy is equal to 0 for x, 5/3 for y, plus, well, the slope is 1, so if you increase y by 1, you increase x by 1. I think that's right. You might have to mess with this. This might need to be something else, but I feel pretty confident about this result. Again, so I will say more broadly, getting 0 as an eigenvalue sucks. It's this weird situation where you have exactly this kind of picture. I would, if you have the time/interest, I would encourage you to plot this system on one of the graphing things to see it really does look exactly like this. You've got all these arrows parallel to each other shooting in towards that other line going that way. So kind of neat, kind of a pain. Next week, we'll start talking about all this combinatorics, counting, permutations, combinations, probability stuff. And that'll be the rest. So we're about to like kind of just say now something totally different. Not going to be any derivatives, any like really none of the stuff we've done so far in the quarter kind of relates at all to what we're about to do. So, all right, have a lovely weekend. See you on, yeah. Oh yeah, I will. I do. I think I have a practice exam written up already. I will definitely get it posted before the end of today. Interesting. Yeah. Yep, office hours from 1 to 4 over in CADS. Interesting problem. You're welcome. Yeah, good questions. Yeah, yeah. I don't love that. Yeah, I don't feel like that problem is is very user friendly.
So that, is it? Eigenvalue towards that line?
Well, so there's two eigenvalues. Lambda equals 0 is one of them, which is represented by that line, and then the other eigenline or eigenvalue -6 means that the other eigenline that goes this way points directly towards that, and there's no like noding or spiraling. It's just literally straight lines pointing inward. So all of your direction vectors just point that way or whatever that way.
There wouldn't be a way to describe it, I guess.
No, it's not any of the usual things. It's like a degenerate system.
Determinant is negative. It's the sound.
Yes. Always, which is always great because then you don't have to do anything else.
Because I wrote wrong on my notes.
Oh. So again, there's a great picture on page like 560 in your book, which shows you where all the spirals and nodes and saddle things are based on the trace and determinant. You're welcome.
Oh.
So there's like 1, 2 days, like the ATC tutors. So they were like, I want this together. Like, we don't know if it's
Which one?
ATC tutors are like freaking out too.
For like the stuff we were just doing? Yeah, well, there is a problem like that. Like, I don't know if there's an example like that, but there is a problem like that.
Like,
More